What happens if you mix electricity and radio? You get AM and FM stations filling up your radio dial. But you probably know that already. What you might not know is that turning up your portable CD player S volume can introduce hum into your speakers. Turn it up enough, and you might even see your lights flicker. That's because your CD player is emitting electromagnetic interference, or EMI, and although most of us tolerate a little bit of extra background noise, the stakes can be much higher in some situations. In fact, the US government spends millions ensuring that nobody messes with their radio communications. So let's talk about how we manage EMI, because today's technological society depends on it. We can't talk about EMI without first talking about electromagnetism. It is the same thing that makes your headphones vibrate when you crank up the volume on a nearby speaker. Electricity flowing through a wire generates a magnetic field around it. When that magnetic field changes strength or direction, it sends out electromagnetic waves that travel at the speed of light. Those waves carry energy. And if the right device intercepts them, that energy can do something useful like power a wireless router or heat up some food in the microwave. But whether it's good or bad, this process always involves two things: an emitter that sends out waves and a receiver that picks them up. Radio works by taking advantage of these electromagnetic waves. Stations broadcast at different frequencies which carry information encoded as fluctuating wave properties such as amplitude or frequency. Your radio receiver is tuned to pick up only those desired waves, filtering out the rest. But just because your radio is tuned to 88.7 FM doesn't mean it won't pick up anything else. There's a lot more going on in the airwaves than just radio signals. A cell phone tower could be broadcasting within range, or maybe there's an airplane sending out a distress signal. All these signals add noise to your reception, sometimes making your favorite tunes sound a little staticky. But it's not just broadcasts you have to worry about. Every day, electronics emit rogue electromagnetic waves. Whenever you plug something into the wall, it could be emitting enough energy to interfere with your reception, assuming your radio is close enough to pick it up. You could even be generating your own interference by using other electronics while listening to your radio. That is why you sometimes hear static on your headphones while using a laptop plugged into a wall outlet. This phenomenon is known as electromagnetic interference, or EMI, and it can be incredibly frustrating. Ever tried to troubleshoot why your Bluetooth headphones cut out in the middle of a commute? Odds are you were passing by something emitting EMI and your headphones picked up the rogue signal. That is exactly what happened to the Air France flight. For 1,590 crew in 2005, they were approaching their destination when their GPS stopped working and their autopilot disconnected. This turned out to be due to EMI from the plane's malfunctioning anti-ice system, proving that even modern aircraft can be affected by simple interference. In the wrong piece of equipment, EMI could cause an infusion pump to deliver the wrong dose of medication or a pacemaker to stop working, underscoring the need for careful management of EMI. Thankfully, engineering has a few tricks up its sleeve to keep signals separate and prevent interference. Like we said before, anytime electricity flows, it creates a magnetic field. So one way to avoid EMI is to make sure the magnetic fields stay contained. Shielding is one solution. Think of those metal boxes that line many walkie-talkies. They block out external signals by containing the magnetic fields inside. Shielded cables can also prevent interference by keeping the wires carrying electrical signals bundled together and shielded. Devices can better resist outside interference. But if you've ever tried plugging something into a wall socket using a long extension cord, you know that bundling wires can be tricky, especially when they're AC power cords carrying large amounts of electricity. And that's not even factoring in how much harder it is to shield a whole room. For applications where shielding isn't feasible, filters offer another layer of protection. Just like how your radio filters out all but the desired station's transmission, filters can remove specific frequencies from a circuit. They accomplish this by using passive components like capacitors and inductors that pass certain frequencies while blocking others. Even so, there will always be some level of interference in our daily lives. After all, that's just physics. So when you're designing a device to withstand interference, you also want to account for the amount of power it'll emit. Even though a low-power device like a handheld game console won't emit much EMI, it's still possible that a nearby cell phone tower could disrupt its weaker signal. On the other hand, a high-power device like a police radar gun could send out strong enough signals to affect many other devices. That's why high-power circuits often include filtering to keep the signal nice and narrow, reducing the chances of it overlapping with other signals. But whether you're trying to receive a weak GPS signal or amplify a faint radio broadcast, sometimes you need a little extra help to sort through the noise. That's where the last major tool for dealing with EMI comes in: diversity. By having multiple antennas or receivers, you can improve your odds of picking up the signal you want, even if it's buried under a bunch of static. Diversity is what allows planes to navigate even when some of their instruments are affected by EMI. By combining multiple uncorrupted signals, they can reconstruct a complete picture of their surroundings. These tools can be combined to great effect, too. For instance, airplanes use shielded cables, filtering, and diversity to protect sensitive communications. But no matter what tools engineers use, the goal is always the same: make sure the right signal gets through without getting corrupted. But even with these tools, we still need to test that they work before putting any device into the wild. After all, no engineer is perfect. Maybe they didn't account for all the ways a user might employ a product. Or maybe a new regulation means a device needs to be retested. That's why once a product is designed, it goes through rigorous testing to ensure it is not emitting dangerous levels of EMI or picking up stray signals. And it's not just a quality assurance measure. Most countries have laws governing the amount of EMI products can emit. The United States Federal Communications Commission requires manufacturers to declare their products' EMI compliance before they go to market. But proving compliance isn't as easy as reading a manual. Instead, products often have to go through a series of tests to prove they meet the FCC's requirements. This is typically done in anechoic chambers. Anechoic means that it absorbs echoes, which is important because these chambers are used to test devices' EMI emissions. By eliminating echoes, an anechoic chamber ensures that the only electromagnetic waves bouncing around the room are the ones emitted from the device under test. These rooms are usually made of metal to block out external signals and are filled with foam pyramids to absorb any internal signals. The walls and ceiling are often covered in these to reduce echoes to minimum levels. This helps engineers get an accurate sense of the device's EMI profile. It's a crucial step in bringing any gadget to market, whether that gadget is a wireless router or a pacemaker. And it's expensive. 1 hour of time in an anechoic chamber can cost over $10,000. Plus, testing is only part of the cost. The entire process of making sure your gadgets are EMI compliant can cost millions of dollars per product. So it is not surprising that big companies spend upwards of 15% of their R&D budget on EMC, but small companies don't always have those kinds of resources. As a result, a third of small businesses' development costs come from failed projects, including failures due to EMI problems. That's why organizations like the FCC have created alternative compliance pathways. Rather than going through expensive testing themselves, smaller companies can rely on certifications from accredited third parties. Some countries even offer subsidies to help small businesses afford EMC testing. No matter how a company chooses to comply, though, the end result should be the same: electronics that work well with each other. Because while EMI can be a serious threat, we can't just turn off our devices and hope for the best. We have to make sure they play nice in the electromagnetic sandbox. Otherwise, we never get to listen to our favorite tunes on the radio or watch a YouTube video on our smartphones. Thanks for watching this episode of C Show. See you next time.